The most powerful rocket ever built is about to fly again. And this time, everything is different. On May 19th, 2026, SpaceX is targeting the launch window for Starship's 12th integrated flight test. And this is not just another test flight. This is the debut of an entirely new version of Starship called version 3, the most significant redesign the program has ever undergone. New rocket, new engines, new launch pad, new objectives, and stakes higher than any previous Starship flight in history. If you have not been following what SpaceX has built for Flight 12, you are not prepared for how big this actually is. Let us start from the beginning. The last time Starship flew was October 13th, 2025, Flight 11. That mission marked the end of the version 2 era. SpaceX flew a 65-minute suborbital test, hit its objectives, and then went completely dark for over 6 months, while engineers tore down their entire design philosophy and built something new from scratch. 6 months of silence from a program that had been launching multiple times per year is not a vacation. It is a signal that something major is being rebuilt, and rebuilt it was. Flight 12 will launch from a brand new facility. This is the first Starship mission to lift off from Orbital Launch Pad 2 at Starbase in Texas, a completely new launch structure that SpaceX has been constructing for over 2 years. Pad 2 is not just a copy of Pad 1. It is an upgraded version built with everything SpaceX learned from every launch, explosion, anomaly, and catch operation since 2023. It features a redesigned orbital launch mount, an improved flame trench, and upgraded propellant loading systems designed to support higher launch cadence operations. Flying from Pad 2 means that even if Flight 12 encounters issues on landing or re-entry, Pad 1 remains fully intact and ready to support Flight 13 without delay. SpaceX now has 2 independent Starship launch facilities operational at the same site. That alone is a massive operational leap. Now the rocket itself. The V3 Starship stack, officially designated as Booster 19 and Ship 39, is visibly different from everything that came before it. When stacked on the pad, the V3 vehicle stands 124.4 meters tall, approximately 4 feet taller than its V2 predecessor. That extra height is not cosmetic. It comes from enlarged propellant tanks on both the booster and the upper stage, giving the vehicle significantly more fuel capacity. And more fuel means more payload. The V3 Starship, in its fully reusable configuration, is designed to deliver over 100 metric tons to low Earth orbit. The V2 could manage around 35 tons. In a single generational upgrade, Starship's reusable payload capacity has nearly tripled. That number is not a distant target. It is what this vehicle is designed to demonstrate on its path to operational service. But the most important upgrade on Flight 12 is what is powering this entire stack. Every single engine on Booster 19 and Ship 39 is a Raptor 3, the newest, most powerful version of SpaceX's methane-fueled engine that has ever been installed on a flight vehicle. Raptor 3 is not a minor revision. It is a ground-up redesign that produces 250 metric tons of sea-level thrust per engine, up from 230 tons in Raptor 2. At the same time, engineers reduced the engine's dry mass to 1,125 kilograms, down from 1,630 kilograms in Raptor 2. SpaceX achieved significantly more thrust from a physically lighter engine, and through redesigning the entire engine architecture, eliminating external heat shields, integrating regenerative cooling directly into all exposed surfaces, and simplifying production, SpaceX also cut the manufacturing cost per engine substantially. Booster 19 carries 33 of these engines. The combined liftoff thrust from those 33 Raptor 3 engines is approximately 9,000 metric tons of force. For reference, NASA's Saturn V, the most powerful rocket ever flown before Starship, produced roughly 3,400 metric tons of thrust. The V3 Starship booster produces more than 2.5 times the liftoff thrust of the rocket that sent humans to the moon. The Super Heavy booster also received structural changes beyond the engines. V3 reduces the number of grid fins from 4 to 3, but each of the 3 new fins is 50% larger and significantly stronger than its predecessor. Fewer fins means less drag, less mass, and fewer complex actuating mechanisms to maintain. Larger and stronger fins means better aerodynamic control during the boost back burn and landing approach. It is the kind of engineering decision that looks simple on paper, but requires an enormous amount of simulation work to validate before it flies. The Starship upper stage, Ship 39, received an equally thorough redesign. The most consequential change is to the propulsion system. SpaceX engineers completely rebuilt the aft end of the vehicle, deleting the individual engine shrouds that surrounded each Raptor engine in previous versions, and removing the large aft close-out volume that required extensive environmental control to prevent propellant from pooling in dangerous locations. By rerouting fluid and electrical systems and redesigning the aft architecture from scratch, SpaceX achieved roughly 1 ton of mass savings per engine across the vehicle. The reaction control system, The small thrusters that orient the ship during coasting and re-entry has also been upgraded for greater precision and reliability. And the aft flap actuation system has been changed from 2 hydraulic actuators per flap to a single actuator with 3 redundant electric motors, reducing mass and cost while actually improving reliability for the return to launch site maneuvers SpaceX plans to execute on future flights. The avionics on Flight 12 represent another complete overhaul. Approximately 60 custom-designed avionics units are integrated into both vehicles, combining batteries, inverters, and high-voltage electrical distribution into single assemblies, capable of delivering roughly 9 megawatts of peak power across the entire stack. The navigation system has been upgraded with multiple redundant sensors for precision autonomous flight across all mission phases. New radio frequency sensors have been added specifically to measure propellant levels in microgravity, a capability that is critical for the orbital propellant transfer operations that NASA requires before Starship can serve as a lunar lander under the Artemis program. And the camera system has been expanded to approximately 50 views covering the entire vehicle, all fed through 480 megabits per second of redundant, low-latency Starlink connectivity. For the first time in Starship's history, mission controllers will have comprehensive, real-time visual coverage of virtually every critical system on the vehicle throughout the entire flight. Now the mission objectives themselves, because Flight 12 is not just a systems check. SpaceX has loaded this flight with a remarkable set of specific tests. The booster's primary goal is to execute a clean launch, ascent, stage separation, boost backburn, and controlled descent to a soft landing in the Gulf of Mexico. SpaceX will not attempt a tower catch for this flight. The Mechazilla arms have successfully caught the Super Heavy booster 3 times on previous flights, but Flight 12 is the debut of a completely redesigned vehicle. Flying a proven booster catch on an unproven vehicle would be stacking risks unnecessarily. The ocean landing allows SpaceX to validate the V3 booster's flight performance data before committing to a tower catch on Flight 13. The upper stage objectives are where Flight 12 gets genuinely fascinating. Ship 39 will deploy 22 Starlink simulator satellites, roughly double the number flown on previous test flights. These simulators are designed to match the dimensions of the next-generation Starlink V3 satellites that SpaceX plans to deploy operationally once Starship is certified. But the last 2 satellites in the deployment sequence carry a special capability that has never been flown before. Those final 2 satellites will scan Starship's own heat shield from outside the vehicle during the re-entry phase and transmit real-time imagery of the tile condition down to ground operators. SpaceX is essentially building an automated external inspection system, using satellites deployed from Starship to photograph Starship's heat shield in flight. This capability is essential for future missions, where Starship returns to the launch site for rapid reuse, because mission controllers need to assess heat shield health remotely before clearing the vehicle for its next flight. SpaceX has also deliberately damaged the heat shield on Flight 12 to gather engineering data. One protective tile has been intentionally removed from the heat shield before launch, and multiple other tiles have been painted white to simulate missing or damaged tiles as imaging targets during the satellite scan. Additionally, a separate heat shield test involves intentionally removing one tile to measure how the surrounding tiles respond aerodynamically and thermally when there is a gap in the protection layer. Engineers need that data to understand how much heat shield degradation a Starship can tolerate before reuse becomes unsafe. It sounds alarming to intentionally damage the heat shield of a vehicle entering the atmosphere at hypersonic speed, but this is exactly how aerospace engineering advances. Controlled damage in a controlled test, with every sensor recording, generates data that years of computer modeling cannot replicate. During the coast phase in space, SpaceX will also attempt a relight of a single Raptor engine in the vacuum environment. Raptor engine restarts in space are critical for 2 future mission profiles, landing burn on the Moon and landing burn on Mars. Every successful in-space relight is a direct data point feeding the interplanetary mission architecture. Ship 39 will also perform a maneuver to deliberately stress the structural limits of its rear flaps and execute a dynamic banking maneuver designed to simulate the trajectory that future Starships will need to fly when returning to Starbase for tower catch operations. SpaceX is not just testing what the vehicle can do, they are teaching it the exact maneuvers it will need for the operational missions coming next. The stakes for Flight 12 extend well beyond SpaceX. NASA's entire Artemis lunar landing architecture for Artemis III and beyond depends on a version of Starship that can transfer propellant in orbit and execute a precision landing on the lunar surface. None of that is possible without V3 performing. NASA's Safety Advisory Panel report in 2025 specifically flagged that Starship development had struggled during most of that year, and that achieving the necessary progress for a crewed lunar landing within the next few years appeared extremely challenging. Flight 12 is SpaceX's direct answer to that assessment. A successful V3 debut validates the engine, the structure, the avionics, and the pad, all in a single flight. It clears the runway for the orbital propellant transfer demonstrations that NASA needs to see before it can finalize the Artemis 3 mission timeline. The road to Flight 12 has not been smooth. The original internal SpaceX target for V3's debut was January 2026. It slipped to March, then April. The 10-engine static fire on Booster 19 aborted early due to a ground support equipment issue. The 33-engine static fire was cut short at just 1.88 seconds into the test when a sensor fault triggered an abort. A fire broke out during Raptor 3 qualification testing at the McGregor test site in April. An anomaly during an April ground test triggered an FAA mishap investigation that added additional weeks of delay. And the original Booster 18, which was supposed to fly Flight 12, was destroyed during a ground test incident in November 2025, forcing SpaceX to rebuild the entire booster stack from scratch using Booster 19. The delays are real. The setbacks are real. But the vehicle that emerged from those delays is more thoroughly tested on the ground than any previous Starship variant. Ship 39 completed a full-duration static fire on April 14th, the first full-duration upper-stage static fire in the entire V3 program. The FCC granted SpaceX a launch license covering dates through October 2026. The integrated tanking test completed cleanly on May 11th. May 19th is the date. The rocket is on the pad. What SpaceX is about to attempt on May 19th is not simply another test flight in a development program. It is the first public demonstration of what the next decade of spaceflight is going to look like. A rocket 3 times more capable than its predecessor. Engines that produce more. Thrust with less weight and lower cost. A launch pad purpose-built for rapid reuse. An autonomous external inspection system scanning the vehicle from orbit. Heat shield stress tests conducted in actual hypersonic flight conditions. Propellant to delivery simulators for the largest constellation in orbit, and all of it pointed directly at the Moon, at Mars, and at the operational future of human space access. The vehicle is on the pad. The license is granted. The window opens at 5:30 p.m. Central Time on May 19th. 12 flights in, and Starship is just getting started. There is a broader context to Flight 12 that the raw technical data does not fully capture. Every version of Starship that has flown has been different from the one before it. V1 proved the concept could leave the ground and survive staging. V2 proved the booster could be caught by a tower, that engines could be relit in space, and that the heat shield could bring the upper stage back intact. V3 is designed to prove that the vehicle is ready to stop being an experiment and start being infrastructure. The jump in payload capacity, from 35 tons to over 100 tons in reusable configuration, is not an incremental improvement. It is a step change that puts Starship in an entirely different category from everything else that has ever flown. For context, the most capable operational rocket in the world before Starship was SpaceX's own Falcon Heavy, which can deliver roughly 63 tons to low Earth orbit in expendable mode and around 26 tons in reusable mode. V3 Starship in reusable configuration is designed to carry more than 3 times what the Falcon Heavy can carry in reusable mode, and do it at a fraction of the per-launch cost once the production and refurbishment operations reach their full cadence. The moment that performance level is operationally validated, the economics of everything from satellite deployment to lunar cargo delivery to deep space exploration fundamentally change.